Hello everyone. Today we are going to talk about conditional probability when two events depend on each other. So, what do I mean by that? So, let me try to first state a scenario where we can easily understand this. Suppose I have a box and there are five balls in it. So, three of the balls are suppose red, okay, and then I have two balls which are blue. Now, the experiment that we are going to do is first we pick out a ball randomly. Okay, when I pick out a ball randomly, I keep it aside. So I keep a ball aside. Now I pick out a second ball. Now, normally we know that when I pick out the first ball, my chances of getting that ball as red are 3 out of 5 because I have 5 balls, all of equal size, and 3 of them are red. When I pick out at that time itself, my chances of picking a blue ball are 2 out of 5. Okay, so this happens on the first try. Now, if I keep that first ball aside, then what happens? Then, if at second try I want to compute chances of getting a red ball, how do I do that? So, I will have to look into the color of the first ball because if the first ball had been red, then at the second trial, so assuming that the first ball is red, then at the second trial, chances of getting a red ball will be 2 out of 4, correct? 2 reds are remaining and 2 blues, so 2 out of 4. And chances of getting a blue ball are also 2 out of 4. Okay. On the other hand, if the first ball that I got had it been blue, okay, so if first had been blue, then I would have 3 red and 1 blue. So my chances of picking a red ball would be 3 out of 4, whereas chances of picking a blue ball would simply be 1 out of 4, correct? So what it means is that what happens at the second trial depends on the outcome of the first trial or first draw of the ball. Okay. So in this sense, the event of picking a ball first trial and the event of picking a ball on the second try, they depend on each other. Okay. So such events are known as dependent events. Why we have to study dependent events separately? Because the probability structure of the second event changes after happening of the first event. Okay. Hence, we have to study them separately. So the probabilities that we wrote here right now, these probabilities at the second trial, they depend on what happened in the first trial. Hence, these are known as conditional probabilities. Okay, so let me introduce the notation and for the same problem. So we want these numbers. So let me keep it like this. Okay. So suppose A is the event of getting a red ball in the first draw. Okay, A is the event of getting a red ball in the first draw. So probability of A we know is 3 by 5. Okay. Now suppose B is the event of getting a red ball in the second draw. Okay. So let me write here. Suppose B is the event of getting a red ball in the second draw. So from the calculations that we did just now, probability of B given that A has already happened means given that the first ball has been read is 2 by 4. On the other hand, probability of B given that A complement has happened means the first ball had been blue is 3 by 4. Okay, so probability of B changes depending on whether A has happened or A has not happened. Okay, so this probability is known as conditional probability. If we have a situation where probability of B is same as probability of say B given A and probability of B given A complement or for that matter something else, then so if this happens then we say that B is independent of A. Okay, that is probability of probability of B does not depend on whether A has happened or A has not happened. So in such situation we will say B is independent of A. But normally many a times happening of B, chances of happening of B do change if A has happened or if A has not happened. So in such a scenario, we say that the two events are dependent on each other. And in such case, our formula for intersection is modified. So if I want to compute probability of A intersection B, that is written as, so A intersection B means we want probability of happening of A as well as B. Correct? We want both these things to happen. So this would be written as probability of A, that is A has happened, into probability of B given A. Because we want both to happen, so both will happen means first A happens and then B happens given that A has already happened. Okay. So the formula for computing intersection probability of intersection of the two events if the two events are dependent is this. Okay. Of course, in this particular context, A and B they were arranged in such an order that it was easy for us to see how chances of happening of B depend on A. Sometimes both the events may be mutually dependent on each other. So in that case, we can actually write this in other way also. So this could be either probability of A into probability of B given A, or it could be probability of B into probability of A given B. That is also possible. Is it okay? So we could, when we want to compute probability of intersection, it would be probability of one event into probability of other event given that the first event has already happened. Okay. And no order is necessary. It could be A into B given A or B into A given B. Okay. Now let me consider an example. Okay. Suppose we are a manufacturing company and we are getting supplies from two different companies, C1 and C2. From the company C1, suppose we have ordered 300 units of raw material, and from company C2, suppose we have ordered 200 units of raw material. Okay. So out of these 300 units, suppose 10 turn out to be defective. And out of these 200 units, suppose 20 turn out to be defective. Okay, that is the information that we have. Now, I pick up a piece randomly and it turns out to be a defective piece. Then I want to compute the chances that this piece has come from first company. Okay, so let me define the events that are of interest here. So let D be the event that the piece is defective. Okay, let D be the event that the piece is defective. So what are the things, what are things that we know? So we know that if the piece is from company 1, then the chances of it being defective are 10 out of 300. Okay. So probability of getting an item to be defective given that it has come from company 1 is 10 divided by 300. Okay. Because what I'll see, out of all the items of company 1, how many are defective? Hence it is 10 by 300. Similarly, probability of an item being defective given that it has come from company 2 is 20 out of 200. Okay, because 20 were defective out of 200. Now we are interested in probability of deciding whether a piece belongs to company 1 if it has been defective. What are the chances that the defective piece has come from company 1? So the probability that we have is D given C1, D given C2, and the probability that we want to compute is C1 given D. So this is basically kind of reverse of this. Okay. But we just saw the formula, we will use that. So probability of C1 given D, let me go back to the formula that we are going to use. See here. So we saw that probability of A intersection B or B intersection A is same as this, A into B given A or B into A given B. So I would use this part of the equality. Okay. So I have this. Correct. So if I have B given A, from that I can compute A given B. Okay. If I know individual probabilities, of course we have not yet computed individual, but we can compute that. Okay. So let me try to write this. So C1 given D I can write as probability of C1 intersection D divided by probability of D. This comes from that formula because C1 given D into D will be C1 intersection D. And how do I get C1 intersection D? That I can get by other way around also. So C1 intersection D I could write as D given C1 into C1. Okay. So the denominator remains as it is. Okay. Now let me try to explain. So here D given C1 I already have. Do I have probability of C1? Let me check. What information I have? I know that out of total 500 units, 300 are from C1. Okay. So in general, probability that a piece is from C1, if I don't know whether it is defective or not, is 300 out of 500, that is 3 by 5. Similarly, probability of C2, that is the probability of the piece being from company 2, will be 200 out of 500, which is 2 by 5. So actually I know the terms in the numerator. My problem is about denominator. I don't know in general what is the probability of the piece being defective. So let me draw a picture which would help us identify that. So suppose this is my all pieces. We know some of them come from company 1, some of them come from company 2. Correct? So suppose these are the defective pieces. Okay, and outside are non-defective. So those in the blue circle are basically defective pieces. So what we can see here is that if I want to compute probability of this blue circle, that is if I want to compute probability of this, I have to basically add this part, this half, okay, to this half. So this half is, in set theory, what is this? It is common part of C1 with D because the circle is D. So probability of D I could write as probability of D intersection C1 plus probability of D intersection C2. So the total probability D I could break down into parts D intersection C1 and D intersection C2. Remember, this can work only if my C1 and C2 are disjoint. Disjoint means they don't have anything in common. Then only this half and this half of the blue circle will have nothing in common, and hence I can write the total probability of the blue circle as addition of the probabilities of these two parts. Is it okay? Here we clearly know that C1 and C2 are disjoint because every part comes either from C1 or from C2. It cannot come from C1 and C2 both simultaneously. Okay. And now my job is easy because D intersection C1 we know is nothing but this numerator. So it is probability of D given C1 into probability of C1. On the same lines I can write D intersection C2 as D given C2 into probability of C2. Okay, so this becomes, now I can compute this. So D given C1 is what? Probability of defective given that it has come from C1. So it is 10 by 300 into probability of C1 is 300 by 500 plus D given C2 is 20 by 200 into C2 is 200 by 500. So what I am left with is 1 by 50 plus 2 by 50, correct? These get cancelled. So this is 3 by 50. Okay. So probability of a defective item is 3 by 50. There is another way in which I could reach this number here. So I could simply write probability of D as total number of defectives divided by total number of pieces. Correct? Total number of defectives divided by total number of pieces. So total number of defectives is 10 plus 20, that is 30 divided by 500. So I will exactly get the same number, 3 by 50. Okay. By the way, this part where we broke down the probability of defective into defective intersected with C1 and defective intersected with C2, this part is known as law of total probability. Okay, law of total probability. Okay, so I have 3 by 50 and now I can go back to my calculations. Let me go back to the calculations that we were doing. Yes, so this C1 given D we wanted to compute. It is D given C1 into probability of C1 divided by D. So let me write it again. So probability of C1 given D will be this first part D given C1 into C1. So that is 1 by 50. Okay, because we have already calculated that. So that is 1 by 50 divided by the denominator is 3 by 50. That is 1 by 3. Okay. So given that the piece is defective, chances of it having come from C1 are 1 by 3. Okay. So this is how conditional probabilities work and they have lots of applications. So in particular, the way in which we wrote here, so we wanted C1 given D1 and we expressed it in terms of D given C1, that is reversed probabilities. So this result is known as Bayes theorem. Okay, let me write general formula for Bayes theorem because here I had only two events, but we could extend it to multiple events. So let A1, A2, or let me write in terms of the same notation, CIs. Okay. So let C1, C2, CK form a partition of our sample space. What do I mean by partition? By partition, I mean that they are disjoint, that is, they have nothing in common, and that their union means together they cover entire space. Okay, so let me draw some pictures. So if I write this as C1, C2, C3, C4, C5, then this is a partition because nothing is common and together they cover entire thing. So if I say this is C1, this is C2 and I don't give any name to this, then C1, C2 alone don't form a partition because this part of my space is remaining. Similarly, if I say this is C1 and this is C2, that is not allowed because they have something in common. So this is also not a partition, this is also not a partition, this is a partition. So notationally this would mean Ci intersection Cj is empty if I is not equal to j. Okay. And it also means union over all Ci's I going from 1 to k is entire sample space omega. Okay. So Ci suppose form a partition and let D be the event of interest, D be the event of interest, then probability of D given Ci is generally given to us. Using that we compute probability of Ci given D as probability of D given Ci into probability of Ci divided by probability of D. Okay, so this is probability of D given Ci into probability of Ci divided by this probability is basically sum of similar terms. So probability of D given Cj into probability of Cj, this denominator comes from law of total probability. Okay, we add all similar terms here. Is it okay? Bayes theorem has lots and lots of applications, some very basic, some very sophisticated. You might have heard that there is a branch of statistics called Bayesian statistics. That Bayesian statistics depends on Bayes theorem. Okay, so the underlying principle for entire Bayesian statistics inference is the Bayes theorem. One very common and old application of Bayes theorem is to assess the chances of an email being a spam. Okay, so we all know that in our inbox, a new email is categorized automatically as being a spam or being a genuine email. In fact, nowadays we have more advanced classification. We have, for example, in Gmail, we have something called as forums, then something called as updates. So new updates come to that. Forum means if you have subscribed to some Google group, etc., all those emails go to forum. Okay. So how does this categorization work? Bayes theorem is one of the methods that can be used. So one of the simplest ideas initially was while determining whether an email is a spam email or a genuine email, people used to focus on words used in that email. For example, we know that a spam email is more likely to contain huge numbers, like you have won a lottery of this amount, or I have just received this amount and I would like to share that with you, etc. So if I have some huge amounts mentioned in that email, then what are the chances that the email is spam? Okay, so here that Ci would be, so C1 would be event that the email is spam, C2 would be event that the email is genuine. Okay, and D would be something like occurrence of such a huge number or occurrence of the word lottery. So I would compute what is the probability of an email being spam given that it contains the word lottery. I would compute that using this. So what I need is probability of the word lottery being used given that the email is spam. So I have some old emails from which I can compute this probability. Okay, so I have suppose 100 old emails out of which suppose 80 are spam. Then out of those 80, how many use the word lottery? Okay, that way I will compute this probability. Similarly, I can compute probability of the word lottery being in the genuine email by using the data of remaining 20 emails. Okay, and then I can compute this. So, and it need not be restricted to one word. So similarly, I'll compute probability of the word one, etc. And then I will see how many words a new email contains, and that will give me chances of that email being a spam. If those chances are very high, then I'll put that email in the spam folder. If those chances are low, then I'll put that email in the genuine folder. Okay, so this is how Bayes' theorem could be used. Um, that was one of the most basic applications, and as I said, nowadays many advanced applications have come up. But the entire Bayes theorem depends on conditional probabilities, hence it is important that we understand conditional probabilities. I have given you a couple of examples here. Now you can try to construct your own examples and see how it works. Okay, let me stop here. Thank you.